The third example in the series has a function which requires the first derivative test. Check it out here in differential calculus. How do we look for the critical points? Having a given function, take the derivative in order to have the slope. And from the highest or lowest points, the slope is 0. Equating the first derivative to 0, we can look for x. So to complete the critical point, substitute x into the original function to have y. Learning about the critical point, next is to categorize if it is the maximum or the minimum point. That is by looking for the second derivative of y, and then check if y double prime is negative or positive. If it is negative, the critical point is a maxima, or the highest point. And if y double prime is positive, then the critical point is the lowest, or the minima. The function for this example is y as equal to x cubed minus 6x squared plus 12x. Take the derivative of the function to identify the critical points. With a polynomial function, we differentiate terms individually. Dx over dx on the third term is taken as 1. So y prime is then 3x squared with the derivative of x upon dx through chain rule. The second term has a constant negative 6 multiplied by the derivative of x squared, which is 2x. Attach the derivative of x upon dx through chain rule. The third term is 12. Now dx upon dx can be simplified as 1. So y prime becomes 3x squared minus 12x plus 12. Now we have the general slope equation for the function. To look for the critical point, we equate the slope to 0. So 3x squared minus 12x plus 12 is 0. Then, through quadratic formula, x turns to be 2. This is the x-coordinate of the critical point, so half is already identified. Look for the second half by looking for the y-coordinate. So take the original function and plug 2 for x. Y is then solved as 8. So the critical point is at 2 and 8. Now that we know the critical point, we validate if this is a maxima or a minima. We do that by taking the second derivative. With y prime as 3x squared minus 12x plus 12, take d over dx of each term. So dx over dx from the second term becomes 1, and the derivative of 12 is zeroed out. Y double prime then becomes 3 times the derivative of x squared, which is 2x, then attach dx over dx. The second term is negative 12. Again, dx over dx is 1, so y double prime is 6x minus 12. Since y double prime is still a function, plug in x, which is 2. Y double prime then is 6 times 2 minus 12, which gives 0. Since the result is either a negative or positive, this signifies that the second derivative test failed. So how do we verify the maxima or minima? After the second derivative test, use the first derivative test, drawing concavity. At x of 2, where the critical point is located, we assume values on either side. From the left, let's assume x of 0. Place 0 into the slope equation, thereby having y prime as 3 times the square of 0 minus 12 times 0 plus 12. Y prime is then positive 12. Regardless of the numerical value, having it as positive, we can draw the curve from the left of the critical point as having a positive slope. That is, it rises from left to right. From the right side of the critical point, assume another value. Say we assume x of 3. The slope at the right side then becomes 3 times 3 squared minus 12 of 3 plus 12, which is positive 3. Having it as positive, the slope again rises from where it ended at x equal to 2. With the continuous rising of the curve, it shows that there is no extreme, and the critical point is neither a maxima nor a minima.